Hey everyone, and welcome to The Explainer. Today, I'm throwing on my meteorologist hat to take you on a really fun journey into the hidden and honestly, sometimes totally chaotic mechanics of severe weather. We're going to deconstruct the life of a storm, looking way past the obvious rain and lightning to understand the precise atmospheric physics that make the whole shebang happen. So, buckle up because we are heading right into the eye of the storm.
It's kind of wild to think about, right? How does perfectly invisible air turn into a violently destructive storm? Massive thunderstorms don't just appear out of nowhere. They actually begin with a very specific recipe of completely invisible atmospheric ingredients. Well before you even see a single gray cloud in the sky, the atmosphere is already setting the stage, layering different types of air masses on top of one another to create this volatile, invisible powder keg.
So let's look at the first step in our meteorological recipe: forecasting atmospheric instability.
To actually predict storms, we have to look at atmospheric instability. Specifically, those setups where warm, moist surface air is trapped right beneath cold, dry air. For a thunderstorm to develop, we absolutely need rapidly rising air. And for air to rise rapidly, it has to become buoyant compared to the air around it. Okay, let's dive into this incredibly important concept that measures exactly that: CAPE, or convective available potential energy. You can basically think of CAPE as the vital fuel or the engine required for rapid thunderstorm development. Technically speaking, it tells us exactly how much positive buoyancy has accumulated. It's a direct measurement of instability that we use to figure out the maximum upward speed a rising parcel of air is going to hit once it gets moving. Simply put, the more fuel you have, the faster that air shoots up into the sky.
To put that into perspective, CAPE values generally range from 0 all the way to over 3,000 joules per kilogram. A completely stable, beautifully clear day, that might have 0 CAPE. But when we're talking about severe weather, these numbers really matter. Meteorologists are specifically hunting for environments where CAPE exceeds 1,500 joules per kilogram. When you have an environment hitting that 1,500 threshold or higher, the atmosphere is fully primed and loaded for the development of highly dangerous supercell thunderstorms.
But here's the thing, fuel alone doesn't instantly make a storm. We also have to talk about SIN, or convective inhibition. If CAPE is the explosive rocket fuel, SIN is basically the heavy lid keeping it all contained. SIN represents negative buoyant energy. It's a layer of warm air aloft acting as a stable capping inversion. Now this lid is actually absolutely crucial for severe weather because it suppresses early weak convection. It stops the atmosphere from just bubbling away all its energy too early in the day. Instead, it allows all that violent CAPE energy to pool and build up in the lower boundary layer until it's absolutely ready to erupt.
To visualize this invisible battleground, we rely on weather balloon data plotted on what's called a Skew-T diagram. Now, what's really interesting about this slide is the tension it shows. If you look closely at this chart, you can see the warm, deeply moist air mass plotted right near the surface. Just above it, that sharp zigzag line, that is our capping inversion, our lid. And right above that is a deep layer of extremely dry, cold air. This chart perfectly captures a highly volatile setup. The atmosphere desperately wants to overturn, but it's completely trapped by that capping inversion. When that lid finally breaks, explosive storm development begins. Let's move to the next phase and see how this all builds.
So once that invisible atmospheric tension finally breaks, we transition into the physical reality of a thunderstorm. The core building block of all thunderstorms is the thunderstorm cell, and its entire lifetime is surprisingly short, usually just 30 to 60 minutes. Every single thunderstorm cell goes through 3 distinct consecutive phases: the developing stage, the mature stage, and finally the dissipating stage.
Let's start right at the beginning. Stage 1, developing cumulus.
This is the exact moment our invisible fuel finally ignites into a visible cloud structure. The lid is broken, the instability is fully unleashed, and the storm begins to materialize right before our eyes. A rising column of air, driven by all that highly buoyant CAPE we just talked about, pushes upward through the atmosphere. We call this rising column an updraft. As the moisture in this updraft cools and condenses, it creates a cumulus cloud. Fed by that intense vertical energy, this cloud quickly grows upward, looking like a massive, fluffy tower, which meteorologists appropriately just call a towering cumulus.
Now, the defining characteristic of this developing stage is the complete, absolute dominance of the updraft. The force of the air pushing upward is so incredibly strong that it physically prevents rain from falling. So while you might see this massive, dark, towering cumulus cloud and maybe even catch some occasional lightning, there's almost little to no rain hitting the ground during this phase. All those water droplets are literally being held suspended in the sky by the rushing wind. It's pretty amazing.
Moving right along to stage 2, the mature storm. This is it, the main event. When a storm transitions into its mature phase, you are looking at the absolute most intense, chaotic, and violent part of its entire life cycle. We really need to highlight exactly why this mature stage is so incredibly dangerous. During this tiny 10 to 20-minute window, the updrafts reach their absolute fastest speeds. Because of these violent atmospheric dynamics, this is the most likely time for heavy rain, highly frequent lightning, large damaging hail, destructive winds, flash flooding, and yes, tornadoes. Literally every severe weather hazard peaks right here in the mature stage.
So the crucial point is understanding what physically changes inside the cloud to make it so dangerous. As the updraft continues to feed the storm, massive amounts of precipitation finally begin to fall. As these precipitation particles drop, they physically drag air downward with them. At the exact same time, dry air mixing in from the sides of the cloud causes evaporative cooling, which creates dense cold air that rapidly sinks. This creates a powerful downward column of air called a downdraft. So in the mature stage, both massive updrafts and violent downdrafts exist side by side inside the very same cloud.
And this brilliantly illustrates the sheer, towering scale of a mature storm in this cross-section. These systems have unbelievable depth, often reaching altitudes of 40,000 to even 60,000 feet up into the atmosphere. As that cold, rain-cooled downdraft slams into the ground, it forcefully spreads out, creating a pool of dense cold air. The leading edge of this cold pool forms a highly dangerous gust front. It's basically a violent line of straight-line winds that races out ahead of the rain, giving you a stark warning of the intense weather just behind it.
Which brings us to our final act, stage 3, storm dissipation. Ultimately, the storm essentially chokes on its own exhaust. All that intense energy, it's fundamentally unsustainable. Remember that gust front we just talked about? Well, as the storm matures, that cold pool of air at the surface expands further and further outward. Eventually, it pushes out so far that it physically blocks and cuts off the storm's vital access to the warm, moist, buoyant air that was feeding the updraft in the first place. The downdraft completely severs the storm's fuel line.
Without that constant supply of warm, moist air to maintain itself, the updraft collapses entirely. The cloud becomes completely dominated by downdrafts, and the storm simply rains itself out and dies. Now, the rainfall intensity will definitely drop off rapidly during this dissipating stage, but as a meteorologist, I have to give a stern warning here. Lightning remains a severe and highly unpredictable danger even when the storm is actively dying. Do not let your guard down just because the rain is stopping.
As the rain fades away, the dissipating storm leaves behind this massive flat-top structure known as an anvil cloud. This flat top actually forms a little earlier in the storm's life, when the powerful updrafts finally slam into the tropopause. That's the boundary between the troposphere and the stratosphere. Because the air can't push up any further into the highly stable stratosphere, it is literally forced to spread out horizontally. In a typical air mass thunderstorm, this anvil is often highly symmetric, leaving a massive icy umbrella high up in the sky.
And I want to leave you with a fantastic piece of visual weather trivia before we wrap up. Sometimes, hanging from the underside of this dissipating anvil, you'll spot mammatus clouds. These are incredibly beautiful pouch-like clouds that form when ice particles evaporate in the anvil, creating localized pockets of dense, cooled air that gently descend. They look completely surreal and otherworldly, but they are really just the harmless, beautiful remnants of a dying storm. So, the next time you look up after a storm has passed and see that towering, flat-topped anvil cloud spreading across the horizon, I hope you see way more than just weather. Will you wonder about the invisible atmospheric fuel, the CAPE, that stubborn capping inversion, and the explosive updrafts that all work together to create it? Understanding the invisible science playing out above us just makes the sky that much more incredible to witness. Thanks for joining me on this explainer. Keep looking up and stay curious.